Hi everyone. Today we are going to look at binary exploitation. So before we get into the topic of binary exploitation, the first question that must come to your mind should be what exactly is a binary? So I think most of us understand what binaries are without knowing what exactly it is. So whenever you use a computer or you use your laptop or your desktop, you'll be running several programs, and each of these programs is actually called a binary, right? So uh, the main reason why it is called as a binary is because this particular file has only zeros and ones, right? So the idea is that our computer cannot understand natural language, obviously, right? So when you speak in English to your computer, it doesn't understand. And likewise, the computer cannot understand your C programs and your Python programs also, right? So this is something that is that many of us are aware of. So the only things that the computer understands are the zeros and ones, right? So let's try to draw what we have here. So let's assume that this is the computer, right? This is the computer. It could be a laptop or a desktop. Uh, I mean, even if the form factor is different, like the size and the shape is different, ultimately they are all made of the same components. So any computer typically has what is known as a CPU, which is the brain of the computer, right? And this CPU is the one that can only understand zeros and ones, right? So these are the two digits that it can understand. So any program that anyone writes, let's say someone from Windows or Google, or I mean Microsoft, Google or Apple, whatever they write, their programs, even though it is written in some language, like let's say if you're more familiar with C++, it could be C++ or it could be a C program, or it could also be Java and stuff like that. So all these programs somehow need to be converted into this binary code, right? This is the binary format. And once the file is converted into a binary, then it is ready for consumption by the CPU, right? So this is the underlying concept whenever you are trying to run a program. So given that this is the case, what exactly do we mean by binary exploitation, right? So before we get into the exploitation part of it, which is typically done by the hackers, we need to understand uh, what is the underlying vulnerability that hackers are trying to take advantage of. So in order to do that, we will start with a very basic example, which is a code structure example. So I will be sharing these files with you. So the two files that we are interested in are code structure example.cpp. For those of you who are familiar with C++, you'll realize that CPP stands for C++, so this is the extension. So this code is written in C++, and and if you're familiar with programming, you'll also realize that whenever you write a code in a high level programming language, you need to compile it down to a binary, right? So when this file is compiled, it produces this binary called as code structure example binary file, right? Okay, so before I proceed, I think there's one thing that I sort of missed mentioning. So depending on what operating system you use, the binary file can be different, right? So let's try to, this is something that I usually do. So it is hard to visualize what a CPU is and what a computer is and what a program is, right? So what I do is I try to tell the companies that actually do this so that you have a easier way of remembering stuff, right? So when it comes to CPU, which is a very small component, I'm pretty sure none of you would have seen a CPU, right? So you can go back and try Googling and try to see a picture of it. So CPU is actually very small. So the CPU that is running inside your mobile phone is only this small. It's only this small, right? And the CPU that is running in your desktop would probably be this small, right? So that's basically how big a CPU is. There are two companies that do the or that create CPUs. The first one is Intel, which creates CPUs, and then the second company is AMD. So for a long time, these were the only two companies that were doing this. And recently, Apple and Google also started creating their own CPUs, right? So these are the companies that do the CPUs. And when it comes to programs can be written by anyone. So as a student, you can write your own program. And as a company, for example, like Google, if Google is releasing something called Google Meets or something like that, then that would be a program. And the Chrome browser, which is also from Google, right? The browser is also a program, right? And all the things that you see at the bottom, this is my browser, which is the Brave browser. And then you have my Outlook, and then all these are programs basically, right? So these are the different companies that create the programs, right? And once the program is compiled, it produces the binary, right? So what is hidden in all these things is the underlying operating system. So there are three popular operating systems that are used in the world today. The first one, obviously, the one that is also popular in Singapore, is actually the iOS, right? So this is the operating system in Apple machines. And then there is Windows, which is what I'm using right now. And there is also Linux. So Linux is also very popular around the world. Okay, so given that these three are the operating systems, so this program has to be written by a programmer in one of these operating systems, right? And then they will use a compiler to compile the program to a binary. And remember, this binary can only be executed on the computer on which it is compiled. So if this program is compiled on Windows, it can only be executed on Windows. If this program is written and compiled on iOS, then it can only be executed on iOS, right? So this is a very simplified view. Obviously, there is a way by which you can write a program in one operating system and execute in another, but I think we'll not get into that. But this is the idea behind it. So the name of the binary in different operating systems is different. So in Linux, we just call them as binaries. We call them as binary, or we also call them as it's a binary, right? In Windows, it comes with the file extension .exe. So those who are familiar with Windows will know that all the files that you can execute have a .executable extension. And in iOS, also, I think it is just called as a binary, right? So in Linux and iOS, it's called a binary. In Windows, it is called a exe file. So with this background, let's try to look at the code that we have. So this code structure example, since I've compiled this on my Windows machine, this one is actually a exe file. So if you don't believe me, if I actually go to show more options and go to properties, it should show that. Okay, it doesn't show here. Maybe I'll show that it is actually a exe file. Okay, and here is a CPP file corresponding to that. So what I'm going to do next is actually take the CPP file and show you what is inside this file. So I use this code editor or known as Visual Studio Code. This is a very popular program, and I suggest you also install this on any machine. If you're using iOS, you can also use, you can install this on any of these machines. So I'm just going to drag and drop this so that I can view the file. So this is what the file actually looks like. There are a bunch of stuff which I honestly haven't looked into, right? But what is most important here is the main function. So all the C programs and C++ programs will have a main function. So the objective of this program is to introduce you to some kind of structures in C++, like branches, like if and else statements and while statements, which comes under the loop, and then the function calls and creating structures. So these are the four topics that are introduced by the CPP file, right? So each function does this. For example, t1 underscore branches, if I go back and look at what it has, T1 branches has two functions. The first one is if and the second one is switch, right? And if I go to the if statement function, it would be somewhere here. Oops. Okay, this is the if statement function, and you can see that this has a simple if and else statement. Now you might be asking, I already know programming. What exactly am I learning from this, right? So that's a good question. So the reason why we are writing such a simple C++ file is to see how these high level programming language, the C++ statements, actually get converted into a binary, right? So that is the goal of this exercise. So I'm not going to go through the process of compiling this program on Windows because I'm pretty sure each of you would be using a different operating system like Windows, iOS, or Linux. So I'm not going through the process of compilation, but I already have the compiled code right here. So now I'm going to show you what is inside this compiled code. So I want to give you a couple of seconds to think about what what you expect to be inside this file. Okay, if your answer was zeros and ones, your answer is correct, right? So this file actually has zeros and ones inside it. I'm going to use a tool called as IDA Pro or IDA Freeware, right? Whatever you see here. So this is a free software that you can download and use it on Windows. Of course, there are equivalent of the same program on Linux and iOS. Both on iOS and Linux, you can use a program called as GDB. Let me just note it down for you. GDB is a program that you can use on iOS and on Linux. So just try to use this program to do the same things that I'm doing on Windows. So IDA is actually a disassembler, and when I open this, it's asking me whether I want to open a particular file, right? So I'm just going to go to the folder where my file is. It's not this one actually. I think it was under something. Let me check. Right, it's this file, the code structure file. So I'm just going to load this file. Okay, that's fine. It's all fine. Okay, so once I load the file, I get presented with something like this, right? But if I click on the hex view, you can actually see the zeros and ones, or in this case, it's a hexadecimal value, right? So you can see that the whole program is actually a bunch of random characters like CC00, E9, something, something, right? So these are very hard for humans to understand. But on the other hand, the computer understands this very easily because the computer exactly knows what these characters are, right? For example, 0000E9 could actually be asking the computer to add two numbers or something, right? So you'll never know. So this hex view is sort of like the binary view of the entire file. So this is all the instructions that the computer is supposed to execute. So quite obviously, it is very hard for humans to understand this, right? So there should be some kind of a middle ground between the two. So let me present you the two extremes. So the program itself is written by a programmer. So the programmer can understand this, but the computer cannot understand this. Whereas the CPU can understand zeros and ones and also hexadecimal numbers, right? So those two are equivalent. So the CPU can understand that, but it cannot be understood by humans. So there is an intermediate format that both can understand, right? Or rather, it's easy for a programmer to understand this intermediate format. So let's try to open the same file in the intermediate format, and that is this one, this file, right? So you can see that the program that we had open here, right? This is the main function, right? So somehow this entire program got converted into these lines of code, right? So it might be a bit surprising because the original program had so many lines, right? On the other hand, this program has only like 5 or 6 lines, right? So just think about it for a second as to what is happening here. Okay, so for those of you who realize that uh, all this is actually some variables and there is actually a jump instruction, right? So this jump instruction is the equivalent of a function call in our C programming language. So this small piece of code is actually going to jump to underscore main underscore 0. This is the name of the function. And now I'm just going to double click on this to go to jump into the main function. Now you can see the actual main function here. So this is a lot of data to process, right? At this point of time, you guys do not know what these things are and what it actually means, right? So the trick to doing cybersecurity without actually uh, knowing the underlying technologies completely is sort of the fun aspect of it also, right? So the way you go about doing this is to develop some kind of an abstract way of understanding this piece of code. So we know that this is the content of the main function, and this is the equivalent of that in C programming language. So I'm just going to scroll and show you the main function. And this is okay. Let me try to oops. Okay, I hope you can see it now. Okay, so this is the actual function, and these are the instructions that got generated, which are supposed to be understood by the CPU. But as humans, we can read the instructions, but we can't really make sense of it right now. So, in case any of you plan to join NUS for a cybersecurity course, or you do my course, we will actually teach you what each of these instructions actually mean, right? But right now it doesn't matter to you, since you have a challenge to solve. We don't have infinite time, so we are going to quickly see how this piece of code got translated into this. So what I meant by abstract thinking was that you realize that all these are function calls, and all the calls will eventually be translated into call instructions. So you will sort of understand that there are 6 calls right here, and then you have 6 function calls here: 1, 2, 3, 4, 5, and then there's also a system. This is also a function call, right? So there are 6 calls and there are 6 calls here. So these are the statements that correspond to these lines of code. Obviously, if you want to understand the rest of it, again, as I said, you can get in touch with me, right? So now let's go ahead and try to see what each of these things do. This init function, we didn't see it earlier, so I'm not going to cover this, but we did look at the t1 underscore branches function. So this is the second function call, so I'm just going to click on this. But before I click on this, I want to find what is our expectation, right? So this t1 underscore branches has again in turn 2 function calls. So I'm just going to double click on this. My expectation is to see 2 function calls, but here you don't see 2 function calls. There's only one jump statement, but this is called as a redirect jump, right? uh, Later you'll realize, I mean, maybe it's not so important to sort of understand this, but here the idea is that the function is calling an empty function and this function is calling the actual function. Okay, so this is basically our function. Let me quickly go through this. My bad. So this there is some problem here. I will tell you what this is. So this function basically does something with system time, okay? But unfortunately, our function does not do anything with system time. So I took a couple of minutes to actually see where system time is being used. It is probably being used in T0 init, right? So let me just try to find this T0 underscore init. So T0 init is the function that does something with system time, which means that our location of the call is actually incorrect, right? So I'm just going to go back a couple of times, and then so this call statement is actually the first function call, right? So obviously I made this mistake, right? So this is also something that you should remember as a cybersecurity engineer, because most of the times you will not have access to this piece of code, and the way in which the systems actually behave is a bit uncertain. It's non-deterministic, which means that every time you compile the code, the order might be slightly different, because the compiler might do some optimizations. Okay, so now I expect to see this in this function, right? Let me quickly check before I explain it to you. Okay, so this is the correct function call, right? So when I get into this, and then when I get into the function again, right, you can see that this is the content of the function, and this function is nothing but uh, it is t1 underscore branches, and this is supposed to have two function calls. But here also you see three function calls. We are not here to decipher why there is an extra function call. If you want to know more about it, you must do a full course on computer architecture. So that is the place where you will learn all this. But here you can see that the second and the third function calls are the ones that correspond to the if statement and the switch statement. So we will only focus on the if statement. So I'm just going to click on the second function call, and when I go here again into this, you can see that this is let me also show you this. So this is supposed to be a function, sorry, the if statement with the if and the else, right? And this is the code corresponding to that. So here, if you read the code, you can actually see that some set of instructions happen, and then there is a branch. There's a code execution the left hand side, and then there's the right hand side. The left hand side is the if branch one, which is this printf, right? So this is the piece of code that will get executed if the condition is satisfied. And on the other hand, this is the one that will be executed if the condition is not satisfied. And it doesn't matter whether the if executes or the else executes, at some point the return has to happen, right? So just before the return happens, all these statements will be executed, and then it will return back to the original function. Okay, right. So this is an example of how if statement gets translated into a machine understandable code. So this would be a good point to actually introduce you to what these instructions actually mean, right? So going back to our drawing board, uh, as I mentioned earlier, there are three companies that actually, or rather four companies that actually make processors. And these are the guys who say what these instructions actually mean. So these instructions are push, call, something, something, right? All these are dictated by these four companies. So Intel and AMD are the age-old companies, and they use a processor known as x86 processor. And Apple uses a processor known as M1, M2, M3 and M4. I think M4 is the one that is more recent. And Google uses a processor, I think it's called Tensor or something, right? I'm not really sure. Okay, so this x86 processor is the most popular one that is being used in desktops and laptops. So in this processor, there is a guideline on what is meant by this push instruction. And likewise, like push, you also have a add instruction, you have a subtract instruction, and you also have a multiply and divide and so on. So all these instructions are defined in this processor. So if I go back here, there are several instructions. So a long time ago, I used to work for Intel, right? And I'm familiar with a lot of instructions that Intel uses. If you were to ask me what is the total number of instructions that are there, I think that would run into 20,000, 30,000 instructions. It's humanly impossible to remember all of them. But a few of these things are quite easy to remember and also seen in most of the programs. So that is what we will be focusing on. So if you were to take a look at this branch, right? So the way this executes is, I'm also going to show you the code side by side. So there is a if condition, right? If this condition is satisfied, you do something, otherwise you do something else, right? And that somehow gets translated into these lines of code. So we will go back to the drawing board of what a computer actually looks like, right? And I'll give you a very brief introduction to this. So the CPU that I've written here can be zoomed in to a much detailed uh, diagram, right? And let's assume that this is our CPU. I told you that it's a very small component, but internally it actually has a lot of details, and in fact big companies focus entirely on building this very small chip, right? Okay, so this CPU contains a few things. The first one that it contains is it has something like a something called a memory, right? Memory is basically where you store some information. Obviously, when I said memory, the first thing that must have come to your mind is random access memory or hard disk. So these are also memories, but they are much larger in size. So for example, a hard disk is also a memory, and today you can easily purchase 2 terabytes of data, right? And you can store all your photos and your videos and everything into it. And on the other hand, a random access memory is also a memory, but these days you get a much smaller. I mean, it is large, but as compared to a hard disk, it only could be something like 8 GB or 16 GB or something like that, right? You can see that this one is in TB, which is a big number, and GB is very small as compared to that. The memory that is inside the CPU is even smaller than that. So the memory is actually quite small, right? And this memory is also known as a register. Okay, it's called a register. And these registers hold temporary values that are used by the CPU. And apart from the registers, it has what is known as a arithmetic logic unit. So this arithmetic logic unit is the one that can actually perform. You can choose to perform an add instruction, or you can do subtraction, multiplication, division, and a few other operations also, right? So all this is done by the ALU. And the last piece of the puzzle is actually another important item known as the instruction pointer, right? Instruction pointer, right? Okay, so now that we have the three big pieces of the CPU, let's go back to the code and see what exactly it means. So now we said that these are the three parts of the CPU, and we are going to take the example of this AND instruction, right? So the first thing that needs to be done to execute this logic uh, is that someone actually has to send this instruction to the CPU, obviously, right? So CPU needs to know what instruction it should execute. So at this point of time, it may not be very relevant to think of who is sending it, but you can think of it as the operating system that is sending this instruction to the CPU, right? So once the CPU receives this instruction, which is the AND instruction, and then it is saying something called EAX comma 1, right? And then likewise, later you can also see another interesting instruction called add ESP comma 4. So CPU can only execute one instruction at a time, right? Our simple CPU can only do this. So let's first start with the AND instruction, and then there is something called EAX and then 1, right? So once this instruction is loaded into the CPU, this AND part of it, let me get another uh, ink, right? So this AND will actually get loaded into the ALU, right? So it will tell the ALU that I want to execute the AND instruction. And then this EAX is nothing but one of the registers here, right? So it will take the value from this register, that is EAX, and then it will AND it with the 1, okay? So this instruction will take the contents of this register and do a AND operation, the logical AND operation with 1, right? So if you're wondering what exactly is this instruction, where is this coming from, you can actually look at the code here. The condition that we have is current underscore sec. I don't know what this variable is, but whatever it is, this variable is ANDed with 1, right? Now you can sort of guess that the CPU somehow thinks that this EAX is having the current underscore sec value, right? Now to confirm that, we can actually go back to this and see where is this EAX. So just before this instruction, you can see that this piece of word, some word is being moved into the EAX. So this is a move instruction, and you can keep deciphering what this whole thing is doing, right? Okay, so for now, this is enough for us. And once we do this AND operation, something very interesting actually happens. So again, we are going to go back to the drawing board and look at what are known as flags. Right, so I said that these are the three parts. The first one is the register, which will store the values, and second one is the ALU, which will execute some instruction, and the third one is the instruction pointer that will tell what instruction is being executed currently, and the fourth piece of the puzzle is known as the flags. Okay, so flags are nothing but error codes, right? So the flags that are available in a typical CPU, I think there are some 10 or 15 flags. I don't remember all of them. The most important ones are the zero flags, right? The zero flag uh, is nothing but one bit of value. So this value can either be a zero or it can be a one, right? The meaning of this or the reason why this is being used will be clear once we look at the example. So in this particular case, we did a AND operation of EAX and 1, and we also saw that the corresponding C programming code is this. So now let's try to rely on our C programming, understanding of C programming, and try to interpret what exactly this if is doing. So after you perform the result of current underscore sec and 1, the result could actually be a 0 or it could be a 1, right? If the answer is 1, then you will execute the if part of the statement. If the answer is 0, then you will perform the second half of it, right? And it might sort of trigger some relation to the 0 flag at this point of time. So what the 0 flag is doing is, whenever you execute any instruction, for example here and AX comma 1, and if the result of this instruction is a 0, then the 0 flag will be set to 1. So the 0 flag is 1, right? It's saying that the previous operation resulted in a 0, right? Okay, so now let's assume that this AND AX comma 1 resulted in a 0. If that is the case, the 0 flag will be set. Okay, so in our particular example, we are assuming that the result of this is a 0 and the 0 flag is set, and we are expecting the else part of it to be executed, that is a branch 2 to be executed. So now let's go back to the code. Here you can see that there's a JZ instruction. So JZ stands for jump whenever it is a 0. Okay, so this JZ instruction will first check the 0 flag to see if it is set or not. So the 0 flag was 0, right? So I mean 0 flag is set because the previous operation was 0. So this is a 1, which means that this jump is a success, or this jump should happen. So you can see that this short underscore location something something, it will jump to this location, and this IDA tool is automatically telling us that this location 415293 is actually here. So the next line of code that will be executed is this one, which is the if branch 2. So you can sort of realize that this whenever this is 0, the branch 2 is executed, which is expected, right? Which is what we expect. And likewise, if this previous operation, the AND operation, did not result in a 0, right? In that case, this jump will fail. If the jump fails, then the default action for the processor is to skip this instruction, skip the jump, and then go to the next instruction, which is the if branch 1, right? So that is how the whole thing got translated into the machine understandable code. So now this brings us to a logical conclusion that programmers typically write their code in C or C++ programming language or even in Java, and they compile it down into a machine understandable code. And this machine understandable code has machine instructions like push, add, and everything, and these will be executed on a CPU. The CPU is quite complex. I just gave you a very brief understanding of what exactly happens inside the CPU. So there are four parts to it, and the four parts together they will try to execute one instruction. And after they execute, they move on to the next instruction and execute it. So now that we have a very good understanding of how a binary is being executed in a computer, now is the time when we actually look at the security aspect of it. Okay, so when a programmer creates these programs, they do not intend, they do not expect the users to actually go into the binary and see what is inside, right? So what happens is, if the programmers are not careful, they might leave some clues about the program, or some important information that should not be known to the user might actually inadvertently get into the program and get into the binary. So for normal users, this is completely okay. They just double click on the program and execute it on the CPU. But for hackers, this is a treasure trove of information, right? So what they try to do is they try to reverse engineer the binary and try to find if there are some clues or some important information that is unintentionally left by the programmers. So that is where the binary exploitation comes into picture. So I'm just going to give you a few examples of, or practical examples of where binary exploitation is useful. So one example is that of proprietary software. So many softwares that we use today, like Adobe and even the Camtasia tool that I use for recording the video, this is also proprietary. So what programmers of the proprietary companies, right, for example like Camtasia, what they do is they try to embed a license key or a password for accessing the program. So when you double click on the program, it will ask you for a key or a password, and the user is supposed to key in the password, and it will do a check whether the key is correct or not. And only after ensuring that the key is correct, it will allow the users to access the program. So imagine what a hacker can actually do. So if this password is hard coded in the program, then the hacker can look at the binary and try to look into the source code, into not the source code, into the binary, to find out if the key is present somewhere. And if they can find the key from the binary, then they know what the password is, and they can use the program without having a valid license key. Right, so that's a very important binary exploitation. There are other classes of attacks in security known as buffer overflow attacks. Some of you might be familiar with it. Even for buffer overflow attacks, most likely the input that is given to you is a binary file, and this binary file contains instructions like push, add, and all these things. And using this binary file, if you give a specific sequence of input, you can perform what is known as a privilege escalation attack. So what is meant by a privilege escalation attack? I might be a normal user of this computer, and a normal user is not supposed to do certain operations, right? Only the admin user is supposed to have access to everything. So this normal user might actually try to give an input sequence to this program to get the permissions of the administrator, right? So they use the binary, they provide certain inputs to the binary, and all of a sudden they get elevated permissions, right? And with these elevated permissions, they can maybe hack into the other users accounts on the computers and so on. So that is a typical example of a binary exploit. And the last example that I gave was that of buffer overflow. But in this session, we are only going to look at a very simple example of reverse engineering a binary file. Okay, so the second example that I have here is actually the secret file, which contains some secret that is not known to me, right? And there's also associated DLL file. So if you guys are fans of games, computer games, you will probably know what a DLL is, right? But anyway, that's beside the point. So the idea here is that this secret file requires this DLL file for execution. Beyond that, we don't have to know anything at this point. Okay, so this secret file contains some secret that I do not know. So I'm just going to try executing this file. I'm going to open a new terminal in my Windows, and to execute the file, normally what the way we execute files on computers is we just double click on it, right? But sometimes when the files are low level programs, it doesn't make sense to double click on it. Instead, the way to execute that is dot slash and then give the name of the file, right? So I'm just going to, I don't remember the full name, so let me just say tab, and this will autocomplete, right? So when I do dot slash secret dot exe followed by something, right? So it asks for a password. So I'm just going to give the password to be ABCD. And when I do that, it says fail. It means that this is not the correct password. So I can try some other password, right? 1234. Again, this is not the password. So the goal of this exercise is to identify the password and get access to this to the rest of the program, right? Okay, so now that we have the the secret.exe, we are going to use IDA Pro to see what is exactly inside the code. I have already opened this right now. Okay, so this is the secret.exe. Again, this has a lot of functions. It doesn't matter. The one it starts with is actually this piece of code. We've seen earlier that this is the top level jump instruction. To see the actual code, you have to go inside the main underscore 0. So one thing I want you guys to notice here is, in this example, we don't have the source code. So in most of the CTF challenges involving binary, you will not be given the source code. You will only be given the exe file or a executable, and you are supposed to look into the executable and then try to figure out what the secret is. Okay, so let's go ahead and look at the function. So this is the top level function. As with all the functions that we have seen before, there's a bunch of stuff which we don't understand as of now. The only thing that we are interested in is there's a JZ here, right? So there's a jump on 0, and before that you can see that there's a compare instruction. So in the previous code that I mentioned, that we actually went through, there was the AND instruction, and the AND instruction set the 0 flag. But in this case, the compare instruction is going to set or unset the 0 flag. And based on whether this operation results in a 0 or a 1, two paths will be taken. Okay, right. So you can see here that there's a something called argc, right? So this argc actually, let me quickly check. Right. So this argc actually stands for the arguments that you give to the function. So what it is actually checking for is that to see whether the number of arguments that we are giving when executing the function, if it is equal to 2, then the 0 flag will be set. If it is 1, then the 0 flag will be unset. Okay, so the argument should be 2, right? So if you look at the example, you can see that this is the first argument that was given, and this is the second argument. So the argument size was 2, so it was able to get into the execution, right? But let's try with something else, right? Dot slash secret, but without a password. So when I execute it without the password, it says usage crack me something something and then password, right? If you're seeing this, right, you can see here that the jump on not 0, right? So if it is not 0, that means it will get to this part. This is the error handling part where it gives the correct usage for me, right? It's saying that my usage should be in this form. Okay, let's assume that the user is giving the correct input in this way, right? So if that is the case, if everything goes well, this is the piece of code that will be executed. Again, in this code there is some push instruction, move something something, it doesn't matter. And there is some string compare, that's also okay. But what we are most interested in is that there is something called test eax, and then there's a short location something, right? And this seems to be very interesting to us because based on the output of this JNZ, we are taking two parts. One is you found the password, and other one is you failed, right? We obviously failed, right? That's why we got this piece. But on the other hand, in the future, when we give the correct password, we would like to get this one, right? You found the password, congratulations. So in order to do that, Let's go ahead and try to read what this actually does. You can see here that there is a test instruction, right? I don't remember, I taught the course last year, so I don't remember what the test instruction is. So we are going to go ahead and read what exactly this does. To understand this, we start with the last four instructions, right? Starting from call. So obviously we want to check whether the user's given password is equal to or to compare it with the system stored password, right? So that operation is likely being done in call j underscore string compare. String compare will compare the user given string, which could be ABCD, against the system stored password, right? So that is what is done here. And if the two passwords are equal, you will realize when actually looking at the string compare instruction that it will put the result back in the EAX register, right? So this EAX will be 0 when the two strings are equal, right? And if the two strings are not equal, then EAX will not be 0, right? So that's the only takeaway from here. So how do you know this? You just have to search for how string compare gives the output, right? So now the output of this call instruction or the string compare will be put in the EAX, and this add instruction is not relevant to us as of now. The test instruction is basically going to do a AND of this EAX and EAX, right? It will do a bitwise AND of EAX and EAX, and since both of them are 0, the output is also 0. So if the two strings are equal, then the EAX will return a 0. So this will be executed only on when it is not 0, right? So if the passwords are equal, then it will skip and come here, and then it will say congratulations. But on the other hand, if the string compare, the two strings are not equal, which was the case in our run through, right? We gave the password as ABCD or 1234. In such cases, EAX will not be 0, right? And when it is not 0, when you try to do AND of two numbers, the same numbers which are not 0, it will return some non-zero number, and then it will run jump not 0 and go to this short location, this location, and then it will execute the fail procedure, right? So now the goal for us is to divert or reverse engineer or divert the execution of this code such that you can actually say you found the password, congratulations, right? Okay, the first exercise that we are going to do is about diverting the access. So we were supposed to go to this field, but we somehow want to go to the password, right? You found the password. So in order to execute the program inside this itself, the way to do this is you can go to options and sorry, not options, to debugger, and then go to process options, and here you can give the actual parameter that you want to give. So in our case, the password which we wanted to try was ABCD, which is the incorrect password, but it doesn't matter. So I'll just give the parameter to be ABCD, right? Okay. And then at this point, I can just start executing by pressing this play button, right? But if I execute this, it will just run to completion. It won't stop anywhere, right? So I want to be able to stop somewhere here so that I can actually see what are the values that are being passed to the string compare. That is what is going to reveal the actual password to me. So I'm just going to right click on this and then say add a breakpoint. So this breakpoint, it is going to stop at this breakpoint, and after that I can look at the next few instructions to see if I can find the password. So let's try executing this. So it starts this window where you can see the state of the computer when the execution happens. So this is obviously the code that is being run on the CPU, and these are the registers that I told you about earlier. So if you remember this one, you can see here that the CPU has some registers, some ALU, and some flags. So you can see the set of registers like EAX, EBX, and everything, and the flags are also here. The one that we are most interested in is the zero flag, which is the SZF, right? So let's try this. So our execution is starting here, and the place where the branching happens is the jump not zero instruction. So if the not zero is true, then it will continue and then say you found the password. But if it is 0, sorry, if it is not 0, it will go and execute the failure routine. But if it is 0, then it will skip this instruction and go to the next one and say that you have found the password. So in order to advance execution, you can actually press this button called F7. I mean, each tool will have its own buttons, but you don't have to remember it. You can just search for it. So I'm just going to press F7 to advance execution to the next instruction. So this means that this instruction is not yet executed. So you can see that this is a move instruction that is moving some password, some data, right? Some data to the EAX. But as of now, this data is not yet moved to EAX. So I'm going to advance execution, press F7 one more time. Okay, so now after this, you can see the effect of the previous instruction on EAX. You can see that the EAX has some 011 something something, right? So this is actually the password that we are looking for. And if I hover over it, the actual system password looks somewhat like this. The 0DC 39 18 1 and something. It is in a different character set, so we are not able to interpret what exactly it is at this point of time. So if I advance execution to one more instruction, you can see that something else is moved on to ECX, right? So let's see what is moved to ECX. So ECX has another data which is 01183 something, which is looking very similar but not the same. Now when I hover over it, you can actually notice that it is the password that we gave, which is ABCD. You can see 61, 62, 63, 64, and the equivalent of that in ASCII is ABCD, right? So this is our password, this is the system stored password, right? So there's a comparison that happens between them, that is the call string compare, and this will affect the EAX. So you can see right after executing the call instruction, right? So I don't want to see inside the string compare, so I'll press F8 button to skip or rather to not get into the function but just go to the next line. So I just now pressed F8. So the output of the string compare will be stored in the EAX register. So you can see that in the EAX register it is not 0, right? This means that the password is not correct. So now we will go ahead and execute the test instruction. So this is not 0. So when it tries to do bitwise AND, the output is also not 0. So you can see that before this executes, the 0 flag is 0. After it executes also it will be 0 because the 0 flag is not set, right? So there's no effect on the 0 flag. And you can see that the 0 flag is not set, so it will go ahead and execute this one right here, right? So I'm just going to press F7 again, and now you can see that the failure routine is being executed, right? So I'm just going to execute this one more time, but the second time I'm going to do something much more cooler, right? So again I've executed the same thing. I'm just going to skip up to the test instruction. So after the test instruction, the 0 flag was unfortunately not set because the password is not matching, right? But what this tool allows you to do is you can double click on this and set it to any value that you want. So I'm manually going to set the 0 flag to 0x1, which means that I'm sort of indicating that the password is matching, like a hack, right? So I specify this as a hack. So the 0 flag is set, manually set by me. So now I'm just going to execute this JNZ instruction, and you can see that you found the password. This part of the routine is being executed. Okay, so that's basically one of the things that I wanted to show you, right? So what I want you to take home as an exercise is to see how to extract the real password, right? So that is actually quite cool. So you can search a little bit and you can try to find out how to extract the password from this part of the routine. I can't remember where it was. All right, here. So if you're wondering what are these two things, you can actually see that the ECX value is actually related to the EAX value, right? So we saw that some EBP plus argv something is happening. You are storing that in EAX, and after incrementing EAX by 4, somehow you're locating the place where the user's data is present. So just to show you again, right, I'm just going to advance execution to this ECX. So you can see that ECX is 4 added to EAX, right? And ECX is exactly the place where you can find the user's input, which is the ABCD. All right. So one value that we use in comparison is ABCD, and the other value should be somewhere above, right, in the function. And you can actually see that there is something called push offset string 2, and the string 2 in the memory, you can see when I hover over it, it says that in the memory the password that is stored is actually top secret, top secret, right? So if I give this as a password, then I should be able to log into the system, right? So that is what I could get from reverse engineering this. So I'm just going to close this and try this password here, /secret.exe, and then top secret, right? So when I use this, you can see that it says you found the password. Congratulations. Of course, this is a very simplified example, but you can use the same principles on more advanced exercises also. All right, so that brings us to end of this session. Thank you.